2026 A-Level Combined Mathematics Paper 1 Part B, question number 13, Part B. Part A of the same question was discussed in a previous video, link in the top right, and Part C of this question will be discussed in a future video, link in the top right. Part B of this question has to do with complex numbers. The question says, let Z1 and Z2 be elements of the complex numbers. Given this, we are to show that these four identities hold true for Z1 and Z2. The first identity is that Z1 plus Z2 conjugate is equal to Z1 conjugate plus Z2 conjugate. The second identity is that Z1 times Z2 conjugate is equal to Z1 conjugate times Z2 conjugate. The third one is that Z1 divided by Z2 conjugate is equal to Z1 conjugate divided by Z2 conjugate for Z2 not equal to 0. And the last one is that Z1 times Z1 conjugate is equal to modulus Z1 squared. Now, after proving each of these, we are then asked to show that if modulus Z1 equals modulus Z2 equals 1 and Z1 is not equal to negative Z2, i.e. Z1 plus Z2 is not equal to 0, then the value 1 plus Z1 Z2 divided by Z1 plus Z2 is a real number. Now, to start off with this, in order to prove these four identities, I'm going to start by defining Z1 and Z2 in the form A plus BI. So I'm going to say, let Z1 equal A1 plus B1i and Z2 equal A2 plus B2i, where the values A1, A2, B1 and B2 are all elements of the real numbers. Now, the reason I'm defining Z1 and Z2 in this format is because it becomes much easier to prove each of these identities with this format. For example, if we consider the first one, for the first one what we can do is to substitute in Z1 and Z2's values in terms of A1 and B1 and A2 and B2 into this thing and slowly simplify algebraically. So doing so, we can see we can start with Z1 plus Z2 conjugate, and if we substitute in Z1 and Z2, we get A1 plus B1i instead of Z1 plus A2 plus B2i instead of Z2, all conjugated. Now with this, what we can do is to take the real parts of A1 and A2 separately and the imaginary parts of B1i and B2i separately. And doing so, we can see if we take this one and this one to the front, we can write this as A1 plus A2 plus, and if we take the B1i and B2i and factor out the I, we get B1 plus B2 times I whole thing conjugate. Now at this point, we have to use the fact that for any complex number Z of the form A plus BI, the conjugate of Z conjugate, is equal to A minus BI. So basically, the imaginary part becomes subtracted. Now in this case, we can see if we do that, the real part is going to remain as A1 plus A2, but the imaginary part becomes negative, and therefore instead of plus B1 B2i, we have minus B1 plus B2 times I. And with this, what we can do is to now rearrange these into the form A1 minus B1i plus A2 minus B2i. Now the reason we did this is because now A1 minus B1i is simply Z1 conjugate and A2 minus B2i is Z2 conjugate. So therefore, by rearranging like this, we get Z1 plus Z2 conjugate to be equal to Z1 conjugate plus Z2 conjugate. And with that, we have proven that Z1 plus Z2 whole thing conjugate by taking, Z1 plus Z2 first and then conjugating is the same thing as distributing the conjugate among their two additions and writing it as Z1 conjugate plus Z2 conjugate. And with that, we have proven the first identity. Now similarly, if we take the second identity, starting from the left hand side, we can write Z1 times Z2 conjugate and substitute in the value of Z1 and Z2 in terms of A1, B1, A2 and B2. So doing so, we can see we get A1 plus B1i times A2 plus B2i whole thing conjugated. Now if we expand this, we can see inside of the brackets we get A1 times A2, which is A1 A2. We get A1 times B2i, which is A1 B2i. We get B21, or rather B1i times A2, which is A2 B1i. And then we get b1i times b2i, which is going to be b1 b2i squared. Now at this point what we have to do is to use the fact that I squared is equal to -1 and substitute and get the form a1 a2, and instead of plus b1 b2 I squared, we can write minus b1 b2 and take that to the front as part of our real part. And then to that, if we factorize out the i's here, we can write the imaginary part as being a1 b2 plus a2 b1 times I, and then conjugate the whole thing. Now we can see we have again the form of real part plus imaginary part, and therefore applying the conjugation rule, we can directly say that this is equal to the real part, which is a1 a2 minus b1 b2 plus, and then we can put, actually not plus, minus, and then we can put the same imaginary part of a1 b2 plus a2 b1 times I. Now with this, what I'm going to do finally is to take this minus b1 b2 and convert it back into plus b1 b2i, and doing so we can see we get the form a1 a2 minus a1 b2i minus, actually I accidentally put a plus here, minus a1 b2i, there we go, minus a2 b1i and plus b1 b2 whole thing times I squared. Now with this, what we can see is that if you factorize out the a1 here and you similarly factorize the b, or rather minus b1i here, you can see we will get a1 times a2 minus b2i minus b1i times a2, and if you divide this by minus b1i, you will get minus b2i. And factorizing, we can see we get a1 minus b1i times a2 minus b2i, which is simply equal to z1 conjugate times z2 conjugate, and therefore we get z1 conjugate times z2 conjugate. And therefore we have proven our second identity, that z1 times z2 conjugate is equal to z1 conjugate times z2 conjugate. Now similarly, if we move to the third one says that z1 divided by z2 conjugate is equal to z1 conjugate divided by z2 conjugate. So to test this, we're going to do the same thing by substituting in z1 and z2 in terms of a1, b1, a2 and b2. So substituting in, we can see we get a1 plus b1i divided by a2 plus b2i whole thing conjugate. Now to simplify this, we need to know that the best way to do that is to multiply the top and the bottom here by the conjugate of the denominator, which is a2 minus b2i. Now if we do that, we can see we will get a1 plus b1i divided by a2 plus b2i times a2 minus b2i divided by a2 minus b2i, and we can take the whole thing and conjugate it. And since we multiplied by the same exact thing on top and bottom, since this thing is not equal to 0, there is no problem here. But we had mentioned that there's no problem multiplying top and bottom by this value, since z2 is not equal to 0, i.e. z2 conjugate is also not equal to 0. Now with that, if we do this and multiply, we can see on the numerator we get a1 plus b1i times a2 minus b2i, which is going to turn into a1 times a2, a1 a2, and a1 times minus b2i, or minus a1 b2i, and then b1i times a2, which is plus a2 b1i, and then b1i times minus b2i, which is going to be minus b1 b2i squared. So we can write minus b1 b2i squared. Now the denominator, we have the difference of squares here of a2 plus b2i and a2 minus b2i, and if we evaluate that, we can see we have a2 squared minus b2 squared I squared, and since I squared is equal to -1, minus I squared is simply equal to 1, and therefore this evaluates to a2 squared plus b2 squared. So putting that in on the denominator, we can see we have this whole thing conjugate. So this is what we get. We get this whole expression conjugated. Now in this conjugate we can see we have two real terms of a1 a2 and minus b1 b2i, and we have two imaginary terms of a1 b2i, or rather minus a1 b2i and plus a2 b1i. So if I factorize them, we can see we have 1 over a2 squared plus b2 squared times this number, which is a1 a2 plus b1 b2 plus a2 b1 minus a1 b2 times I, and this whole thing needs to be conjugated. Now conjugating this thing, we can see we get 1 over a2 squared plus b2 squared times this other thing on the inside, which is going to be the real part as it is, or a1 a2 plus b1 b2 as it is, and then we're going to have minus this whole thing, which is minus a2 b1i plus a1 b2i, since minus times minus is going to be plus. So we have this whole expression. Now if we take this expression, we can see by factorization this same expression could be written as a1 a2 minus a2 b1, or rather a2 b1i, and then if we take this term and this term, we can write this as plus a1 b2i and then minus b1 b2 I squared, and all divided by a2 squared plus b2 squared, which I'm going to write as a2 plus b2i times a2 minus b2i. Now if we consider what we have here, we can see by factorization on top there's a common factor of a2 in these two, and factorizing that we get a2 times a1 minus b1i. I've forgotten the 1 here, a1 minus b1i, and on here we can see we have a common factor of b2i, and factorizing that we can see we have plus b2i times a1 minus b1i. Now considering that, we can see on top we have that, and on the bottom we have a2 plus b2i as one factor, and we also have a2 minus b2i as another factor. Now considering that, we can see on top we have the factor of a2 plus b2i, and on the bottom we have the same factor, and if I factorize that out, we can see we have a2 plus b2i times a1 minus b1i divided by a2 plus b2i, same exact thing, times a2 minus b2i. And if we divide these two, since they're not equal to 0, they can be cancelled, leaving us with a1 minus b1i divided by a2 minus b2i, which is equal to Z1 conjugate divided by Z2 conjugate. And here we have to mention that this can only be done because Z2 is not equal to 0. And with that, we have shown finally that Z1 divided by Z2 whole thing conjugate is the same as taking Z1 conjugate and dividing by Z2 conjugate, provided that Z2 is not equal to 0. And with that, we're done the third proof. Now for the last one says show that Z1 times Z1 conjugate is equal to modulus Z1 squared. Now for that, if we go down and substitute, what we will do is to do Z1 times Z1 conjugate, which is going to be a1 plus b1i times a1 plus b1i conjugate, which is going to be equal to a1 plus b1i times a1 minus b1i, which if we multiply is the difference of squares of a1 squared minus b1 squared I squared, and I squared is equal to negative 1, so therefore we have minus I squared here, which is positive 1, which means we have a1 squared plus b1 squared, and a1 squared plus b1 squared is exactly the value of modulus of Z1 squared, since modulus of Z1 is equal to the square root of its real value, which is a1 squared, plus its imaginary value, which is b1 squared. And therefore, we can see directly that Z1 times Z1 conjugate is equal to modulus of Z1 squared. And with that, we are done with the 4 proofs. Now, after the question then says, show that if modulus of Z1 equals modulus of Z2 equals 1, and Z1 is not equal to negative Z2, then this whole value here is a real number. Now further what we're going to do is to consider the information we're given and consider what we can say based on the information we're given. So we are given modulus z1 equals modulus z2 equals 1, and we're also given z1 not equal to negative z2, and with this we have to show that 1 plus z1 z2 divided by z1 plus z2 is real. Now if we consider what a real number actually is, in the complex plane, a real number is a number that lies on the real axis. If we have the real axis here and the imaginary axis here, a real number is a number that is somewhere on the real axis. Now to be on the real axis, you need to have your imaginary part being equal to 0. So therefore, if a real number is expressed in the form z equals a plus bi, then b is equal to 0. Now if we just consider what the conjugate of this number would be, the conjugate would be z conjugate equals a minus bi. Now since b is equal to 0, the first term here is equal to a. And since b is equal to 0, the second term here is also equal to a. So what this means is that if your number is a real number, then the number is equal to its conjugate. Z is equal to z conjugate if z is a real number. Now taking from that, what we can do is to try and equate this number with its own conjugate and see if both sides are equal. If both sides are equal, then our number will in fact be a real number. So that's exactly what we're going to try to do. So to start off, I'm going to write the condition that if a complex number, and let's say the complex number is z, if a complex number z is real or an element of the real numbers, then as we discussed, z must be equal to z conjugate, or rearranging, we can get the equation z minus z conjugate equals 0. Now this right here is the condition that I'm going to be using in order to check if this number right here is a real number. So what I'm going to do is to take this number and substitute it in instead of z and see what we get. If we get 0, then we can conclude that this number is a real number. So substituting in, we get this number minus itself own conjugate. So we have this number minus itself conjugate. Now in order to simplify this down, what I'm going to do first is to go up and use these three identities in order to distribute the conjugate that we have on this number right here. So if we use that, we can see we have a numerator and denominator which will be distributed as 1 plus z1 z2 whole thing conjugate divided by z1 plus z2 conjugate. Now after that, I am then going to use the addition formula to distribute the conjugate on top and bottom as conjugate of 1 plus conjugate of z1 z2 divided by conjugate of z1 plus conjugate of z2. Now in this case, I am actually not going to use the bottom distribution, but I am going to distribute the top. So therefore, I'll distribute it as the following. Now here we have one conjugate, and since 1 is a real number, one conjugate is equal to 1, and therefore I can just cancel this conjugate and write this as 1 plus conjugate of z1 z2 divided by z1 plus z2 conjugate. Now after that, I'm going to do one more thing. I'm going to use the multiplication formula to distribute this as z1 conjugate times z2 conjugate. And after that, I'm going to take this value and substitute it in instead of the expression that we have over there. So substituting this in, we can see we have this expression for this number, and then we have the other number as it is as this expression right here. So we have that minus 1 plus z1 conjugate times z2 conjugate divided by z1 plus z2 conjugate. So this is the expression we get. Now from this expression, what I'm going to do next is to take a common denominator of z1 plus z2 times z1 plus z2 conjugate. So doing so, we can see we get 1 plus z1 z2 times the denominator, which is z1 plus z2 conjugate, minus this bit, which is 1 plus z1 conjugate times z2 conjugate multiplied by this one's denominator of z1 plus z2, and everything is divided by the final value on the bottom, which is z1 plus z2 times Z1 plus Z2 whole thing conjugate. Now, if we consider what we have here, we can see on the numerator, we have a bunch of terms that if we're lucky, will cancel to become 0. But at the denominator, we have a number times its own conjugate. So if this is a number times its own conjugate, we can see the denominator is equal to the numbers modulus squared according to the fourth identity that we had over here. So according to that, we can write that this is equal to Z1 plus Z2 modulus squared. So we have Z1 plus Z2 modulus squared, and at the numerator we have all of this stuff to expand. Now to expand this, what I'm going to do is to first distribute this conjugate as Z1 conjugate plus Z2 conjugate like so, and then I'm going to multiply through everything. So multiplying through everything, we can see we have 1 times Z1 plus Z2, which is going to be equal to Z1, or rather Z1 conjugate plus Z2 conjugate, which is going to be equal to Z1 conjugate plus Z2 conjugate. And then we have Z1 Z2 times Z1 conjugate and Z1 Z2 times Z2 conjugate. So therefore, we are going to have Z1 times Z1 conjugate times Z2, and we're also going to have Z1 times Z2 times Z2 conjugate. Now in addition to that, we also have all of the terms that are coming from the other part on the right hand side. We have all of the terms coming from this. So to consider that, I'm going to make this bar longer, this vinculum longer, in order to have enough space to actually accommodate all of the terms. So the next term we have here is minus 1 times Z1 plus Z2, which is equal to minus Z1 minus Z2. And then we also have minus Z1 conjugate times Z2 conjugate times Z1, which is going to be equal to minus Z1 conjugate times Z2 conjugate, and also we have minus Z1 conjugate Z2 conjugate times Z2, which is minus Z1 conjugate times Z2 conjugate. So we get this expression right here. Now, in this expression, we can see we have a bunch of Z1 times Z1 conjugates here and here, and we also have two Z2 times Z2 conjugates here and here. Now, using the fourth expression that we had over here, I'm going to simplify them into this form where we have modulus of the number squared. So doing that, we can see from this expression, we get Z1 conjugate plus Z2 conjugate plus Z1 modulus squared times Z2 plus Z1 times Z2 modulus squared minus Z1 minus Z2 minus Z1 modulus squared times Z2 conjugate, and then minus Z1 conjugate times Z2 modulus squared. So times Z2 modulus squared, and all of that is divided by the modulus of Z1 plus Z2 squared. So divided by modulus of Z1 plus Z2 whole thing squared. Now in here, if we go back to the conditions they gave us, they told us that modulus of Z1 is equal to modulus of Z2 is equal to 1. So therefore, this is equal to 1, this is equal to 1, and this is equal to 1, and this is equal to 1, since 1 squared is equal to 1. So therefore, if we simplify, we can see we get Z1 conjugate plus Z2 conjugate plus 1 times Z2, which is Z2, plus 1 times Z1, which is Z1, minus Z1 minus Z2 minus this bit right here, which is 1 times Z2 conjugate, so minus Z2 conjugate, minus this bit right here, which is minus Z1 times 1, which is going to be equal to minus Z1 conjugate. Now all of that is divided by the value Z1 plus Z2 modulus squared. Now considering this expression, we can see on the numerator we have Z1 and minus Z1, we have Z2 and minus Z2, or rather Z1 conjugate and minus Z1 conjugate, Z2 conjugate and minus Z2 conjugate, and we also have Z2 minus Z2 and Z1 and minus Z1. So all of the terms on the numerator cancel, which means on numerator we have 0. So on top we have 0, and at the bottom we have modulus of Z1 plus Z2 squared. Now the only way in which this will be equal to 0 and not have a problem is if modulus z1 plus z2 squared is not equal to 0. But that is the case, and in fact this is equal to 0 because z1 plus z2 modulus is not equal to 0 as z1 plus z2 is not equal to 0 as z1 was given to be not equal to negative z2. So because of this we can conclude that our final answer here is equal to 0. Now we can say since the number and I'll just copy paste the number because I'm too lazy to write it again. This number fits the form, and we'll write the form of z minus itself conjugate equals 0. We can conclude that therefore the number is an element of the real numbers. So this number is a real number, and with that we are done with this question. Now finally, let's go up and discuss the marks award for this question. So at the start of the question, when you take these four identities and try to solve them, for the first one, when you apply the conjugate like this, you get 5 marks, and when you get the final correct answer, you get another 5 marks. For the second identity, when you take these two, distribute them, apply the conjugate correctly, you get 5 marks, and after that, when you then rearrange and simplify to get this answer, you get another 5 marks. Now after that, for the division one, when you do the division and then multiply the top and the bottom by the conjugate like so, you get 5 marks for that, and simplifying this down, when you then get the final correct answer, you get another 10 marks. Now after this, for the last one, in this identity, since there's not much to prove, when you get the final answer, you get 5 marks. After that, for the second part, when you then take this number and then say for any complex number, if the complex number is a real number, then z will be equal to z conjugate, and therefore z minus z conjugate is equal to 0, and then when you apply that condition to this number, you get 5 marks for that. Now after that, when you simplify down and get to this point, from this point, when you apply the fact that modulus z1 and modulus z2 are both equal to 1 and get them from here, substitute them all with 1 to get to this point, you get 5 marks. After that, when you then cancel everything and get 0, and then conclude that therefore, since the number was in the form z minus z conjugate equals 0, this number must be a real number. For the conclusion, you get another 5 marks. And that is the end of this question. So I hope you enjoyed. If you had any feedback or questions, post them in the comments down below. Thank you for watching, and goodbye.